This is a production of Cornell University.
Okay, hi, so my name is Leilah Krounbi, and I'm going to talk to you about a project that I've been working on regarding biologically and thermochemically altered human waste, converting it into fertilizers and soil conditioners. I became involved in this project through a broader initiative that was put out by the Gates Foundation called the Reinvent the Toilet Challenge. I was sort of very low on the totem pole in terms of people that were involved. There was a project called the Climate Foundation, which was awarded one of these prizes for developing a pyrolysis-based toilet. So it's a toilet that takes the solid waste and converts it into charcoal. And they contacted Johannes Lehmann and they asked him to be involved, and then I somehow got involved. And the goal of this call was to generate waste management systems that are off the grid, so basically non-water-based waste management systems, which is particularly important in developing countries where sometimes the population density in informal settlements is so high you can't even put in infrastructure. And obviously, one of the objectives is to remove germs and recover valuable resources such as energy, clean water, and nutrients. And this is where Johannes and I came into the project. We were working on converting the or assessing whether the charcoal was a valuable resource with regards to nutrients. And all project proposals had to demonstrate that their plan cost less than 5 cents per user per day, and it was supposed to promote sustainable services in poor urban settings. So this is the context in which I've been working on my dissertation. And this is the physical context in which I worked for about a year in Kenya. This is a picture from Kibera. It's one of the most, renowned or nefarious, slums in Kenya. It's not the biggest and it's not the worst, but this is a common sight because waste management is generally by just an open disposal, so open defecation, open dumping, and what you have is a problem with an excess of nutrients. But actually, this problem with an excess of nutrients in urban areas is common all around the world. I think we all understand that there's a decoupling between the nutrients generated in concentrated areas of human environment or where animals are produced, where animals are grown, and areas where crops are grown. I mean, even in the Northeast, you have this problem where areas where there are large dairy farms, you have a large concentration of nutrients in areas where people are growing maize. They're applying tons of mineral fertilizer because there's this decoupling. And this is particularly prominent in developing countries where there's absolutely no way, so there's no waste treatment at all. It just goes into the ambient environment and it just stays in the waterways around Nairobi. And this problem of excess, it manifests as excess pathogens and health problems, excess nutrients loading into the water, and excess greenhouse gases. Whereas over in Western Kenya, where a lot of the maize is grown, you have the opposite problem. You have a deficiency. You have a soil fertility deficiencies. People can't afford to buy fertilizers. They don't have access to them, which result in yield deficiencies, and they cause human nutritional deficiencies. And here you can see what a little bit of fertilizer can do for a crop. This is a maize plot that's not receiving any fertilizer, and this is a maize crop that's receiving only 80 kilograms of nitrogen per hectare. And so if we could just try to couple these systems, take some of this excess and put it here, we might really be on our way with helping people. And so our collaborators on the ground in Kenya that were also involved in this project are a latrine project started by some MIT business students that basically recognized a business opportunity in waste management in the slum called Sanergy. And their business model is to sanitize waste by collecting it, transforming it, which is we're in the business of transforming waste and generating either energy or some valuable product. And they're located in Nairobi, Kenya, and their latrine system, it operates. It's called a urine diversion system where the solid waste is collected and one portion of the liquid waste in one. And that's very important when you're sanitizing waste because most sanitization processes involve heat. I mean, there are some that don't, like anaerobic digestion or fatty acid, things that Lars Angenet's lab is working on. But our method, thermochemically transforming waste, and also compostation, they necessitate heat. And so you don't want, you want as low of a water content as possible. And also what you get are two resources. You get the solid portion of the waste and the liquid portion of the waste, and they have different benefits. when they're processed properly. And at present, Sanergy is only processing waste through compostation, and that's sort of where we came in. We were trying to see if pyrolysis was another, maybe a more efficient solution for them. And I just want to know, so this is from their website. So at present, I just downloaded this yesterday. They have 932 active toilets. They sell the latrines to people that then operate them by pay. It's like 15 cents to use them. And then they have about 50,000 users a day. So I'm going to use that number to calculate basically what the potential nutrient recovery would be from these 50,000, I call them fresh life poopers, because the latrines are called fresh life latrines. So here's somebody using a fresh life latrine, and he's generating on average 50 grams of dry human waste per day. That's sort of the values are all over in the literature, but this is what we measured at Sanergy. This is what we measured coming out of the latrines based on the people that were using them. And in that 50 grams of dry human waste a day, based on the nitrogen, phosphorus, and potassium content that I measured, we can generate about 1.4 grams of nitrogen, 0.5 grams of phosphorus, 0.5 grams of potassium. And in the urine, people generally excrete about 1 liter a day, which on a mass per volume basis is about 1% nitrogen, 0.7% phosphorus, and 0.2% potassium. We have 10 grams of mineral nitrogen, 7 grams of phosphorus, 2 grams of potassium. So we add that up, and we want to convert that into how many farms we can fertilize per year from those 50,000 fresh life poopers. So what we get over 1 year, if we just account for the nitrogen in the urine, which we know is plant available, we get about 183 tons per year just from those 50,000 people, 155 tons of phosphorus, 46 tons of potassium. And with that, we can fertilize. These are the fertilizer nutrient recommendations for the Ministry of Agriculture. I understand that that's very low, but you have to understand that people are applying 0. So 90 kilograms is a lot for a farmer in Western Kenya. We can fertilize over 2,000 farms a year just using these 50,000 people, just using the waste generated from these 50,000 people. And that's great. So another question is, well, why pyrolysis? There's so many other ways to sanitize waste. You can just do composting, you can do anaerobic digestion, you can do this, incinerate. But the thing about pyrolysis is that, first of all, I think you understand that people are interested in it because of its energy, its efficiency with regards to energy. It's kind of exothermic to a certain point under certain conditions. But I think in this context, it's important to consider that right now, Sanergy, they're just using composting. So these are windrows at Sanergy. And you have to get, for thermophilic compostation to work, you have to get up to 60 degrees Celsius. And Nairobi is actually a kind of a cold place. It's like high up, it rains a lot. And I've been told that they can rarely get above 55 degrees Celsius, so you have to leave it out for about 9 months. But with pyrolysis, these temperatures assure sanitization in a very short time, within a day. I mean, the goal of the Reinvent the Toilet project, the people we were working with, was to convert 2 tons of waste a day into char. Like that was the plan. And the anoxic conditions, so pyrolysis is like incineration with no oxygen. The anoxic conditions reduce carbon, so carbon becomes reduced and less, less microbially available or more persistent in soil. And it concentrates nutrients, because what goes off during the process is carbon, oxygen, hydrogen, and you get a concentration of the plant essential nutrients. It requires obviously less time and less land than compostation. And I wanted to show this data just because I know that there are a lot of issues with biosolids, and I'm not for biosolids, and this is not biosolids, this is not mixed with industrial waste. And I wanted to also show you that the problem with pollutants in Kenya is not coming from people, with regards to heavy metals. Obviously, I did not measure xenobiotics. And anyways, with pyrolysis, that wouldn't be a problem. But with regards to heavy metals, just leaving the waste in the environment increases the concentration of lead and arsenic relative to treating it immediately. And this is what we did. We took this and treated it immediately. We have much lower lead concentrations than the compost that was sitting out for months. And that's just because of the ambient environment. It's very polluted in Nairobi. And so the treatment methods that I'll be talking about in this presentation, I call them biological sanitization, which is composting. There are other methods for biological sanitization, like anaerobic digestion, which I'm not going to talk about. And I'm going to talk about thermochemical methods, so including torrefaction at 200 degrees. But this doesn't really alter the chemistry of the material. It mostly serves to desiccate it, but it's still anoxic, and consider that. And pyrolysis, which is thermochemical transformation between 300 and 700 degrees Celsius. So the research questions that I'm going to address right now are, let's start with the first one. Which properties of treated human waste have agronomic value? So what is it about this material that might improve crop yields? I mean, is it the surface area? Is it the phosphorus? Is it the nitrogen? Is it something, you know, rhizobia? I didn't test all these things, but I'm just interested in getting an idea of, is there anything valuable about this material? And particularly, I wanted to try to convert some of the agronomic properties into a monetary value relative to the price of fertilizer. And I tried to quantify not just the nutrients, but also what I considered to be soil conditioning properties. I was also interested in whether the nitrogen and the phosphorus is available in these different amendments in soils and whether it differs across soils. So if I incubate these amendments in soils, what happens to nitrogen and phosphorus availability? And so to that end, I incubated them in soils that differed in pH and texture. And my third objective, having a general idea that most of the nitrogen in the waste was probably not plant available, I wanted to see if I could incorporate the nitrogen in urine into pyrolyzed human waste to produce a high-value soil amendment, knowing that nitrogen is first and foremost the most limiting nutrient. Obviously, there are so many other limiting nutrients, but I feel like, you know, the low-hanging fruit of taking care of a lot of plant issues is adding nitrogen. And so I tried to develop a process for precipitating nitrogen from urine into pyrolyzed human waste, not relying on necessarily the chemical properties of the waste, but just trying to create a solution environment that could happen, within which that could happen. So here, my first objective, determine the agronomic properties and values of human solid waste. So when I say agronomic properties, I'm talking about things like plant essential nutrients like phosphorus, magnesium, potassium. I'm also talking about properties like liming. Can this material consume acidity? Does it have carbonate? It's sort of embedded in the matrix. What about nutrient retention? Is it sorbing, you know, calcium? What about nitrogen? And also, is it a source of stable carbon? And stable carbon is important, we know, from, you know, like soil health, because it actually affects these things, liming and nutrient retention, but it also is important from an environmental perspective. We want to mitigate the oxidation of waste, because at this point, the waste is just going into the ambient environment and completely oxidizing or being converted to methane. And we would like to stabilize some of that carbon. So the goal is to take this weak little plant, add a little charcoal, and get a nice looking plant. All right, so to start, I had to create some human waste charcoal. So me and some people, not this guy, but some other people, I took this from the internet, but we collected some waste. So these are the buckets that you collect the solid waste in from the toilets and the jerry cans with the urine. We collected that, and I just want you to know that it's the human waste is very different than like biosolids, which has a very high concentration of bacteria, because it's, you know, undergoes digestion, and it's not like pig waste, because it's actually, because of the way that people use the latrines, they put sawdust as a cover material. It's mixed with sawdust, like mostly eucalyptus, at a 1-to-1 dry volumetric ratio, and so it looks like this, and it's a little bit more like animal, like cow manure almost, like the texture. And so we had to sun dry it to get it below 35% moisture, because again, we're thermochemically transforming it, so we need to have as low of a water content as possible. We pyrolyzed it in a unit that actually Akio sent to the collaborators, and then we did some analyses. And those analyses included, we extracted macronutrients. Well, first of all, we extracted nitrogen with potassium chloride. We wanted to get the plant available nitrogen, not just the total nitrogen. And then we just did a Mehlich extraction of these macronutrients and these micronutrients. Very simple, just to get a sort of a proxy for what the nutrient availability would be in this material. And then I looked at the soil conditioning properties, which again I determined would be the liming potential, which is I calculated as the calcium carbonate equivalency using a back titration with sodium hydroxide. And then I tried to quantify, I basically used the cation exchange capacity to assess how much of the base cations in the material could be retained over time. And I tried to quantify that, turn that into a metric that actually is just in milligrams per kilogram of nutrients. And then I tried to quantify the stable carbon expected to remain after 100 years. I called it BC plus 100, using a metric which is the molar concentration of hydrogen to organic carbon, which is sort of like a metric for the aromatic carbon versus aliphatic carbon. So it's the organic carbon that you would expect to remain in the soil. And this is what I got. So this top graph, the y-axis is the nutrient concentration in each amendment. Amendments being the compost, the torrefied waste, the 2 pyrolyzed waste at 2 different degrees. The nutrients being the extractable nitrogen, these nutrients, micronutrients, and then CEC is the contribution of CEC towards nutrients by retaining what the potassium, calcium, magnesium that's already in the soil, and I have a calculation for that, and I didn't show it, but I can show anyone that's interested. And so what I can see here is that as I increase with highest heating temperature, I have more nutrients because the nutrients become concentrated. Because actually, there's a yield loss, a mass loss with as the product is subjected to thermal treatment. So at 500 degrees, I actually only am retaining 30% of the original mass, and most of what's lost is carbon, oxygen, and hydrogen. So the nutrients are concentrated. Nevertheless, even though I've still lost, maybe 70% of the carbon or hydrogen and oxygen, I still have, well, I didn't lose 70%, I still have 70%, according to this metric, of what could be considered persistent carbon in this material compared to all the other materials. And so in conclusion, the pyrolyzed human waste at 500 degrees, it contains about 15% more nutrients than torrefied waste, 100% more nutrients than composted waste, and about 600% more stable carbon than either of these. And that can translate into a monetary value, and now we're going to calculate that. So to put a dollar sign, I just took fertilizer and lime prices from different sites, from this really nice site that has prices for fertilizers in East Africa as well as international prices, and good old Alibaba. And I also calculated I tried to put $1% on the stable carbon using discount prices from a World Bank report that I used 20 different countries to average out what a carbon discount rate would be. And the amount of money per amendment is basically the summed value of all the agronomic components, including the nutrients, including the liming, including the stable carbon. And again, I mean, as you guys know with prices, especially when you're talking about Africa, international over time, there's a huge sensitivity of the amendment value on the market prices. And so the quartile values are really all over the place. So I just looked at the median market price for all of these nutrients. And so what I got is this. So first of all, I just want to say, so the y-axis is US dollars per ton of what? So here it's per ton of feedstock, per ton of the initial waste before it's treated with anything. So everything's been normalized to what I call the yield, like the mass yield coming out of the treatment process. And so what you can see is as the material is subject to higher heating, there's more mass lost, and that decreases the value of the waste. Basically, it's what the waste processing plant sees. It's what they feel. They feel they have less material, they're getting less money because they have this mass loss. This is US dollars per amendment, US dollars per ton of amendment of the final product. This is what the farmer sees. So if you give a farmer a bag of this is what they see. They see all this phosphorus and potassium, and so it has a very high value, but they're also not paying for the overhead costs. So I just want to demonstrate that there are two ways to put a dollar value on this product. It's either what is in the hands of the farmer that would otherwise have been buying fertilizer, or what is in the hands of the waste processing that has to sell the amendment. And if you are just the farmer, you'd much rather have the higher temperature material because it has more nutrients in it and you're going to save money. If you're the waste processing plant, you'd much rather process this material because you're getting more money per unit mass that you're collecting. And I also want to point out that there's really, the big difference here is just between the thermochemical treatments and the biological treatment. I mean, it's just completely different, and I think that's because the compost is not really like the feedstock anymore. I think it's been contaminated with soil. It has a very high concentration of iron, aluminum, and manganese because it's sort of been mixed in the windrows. Whereas the 200-degree material is the most similar to the feedstock. So I just think that the composting process fundamentally changes the material. I mean, they all fundamentally change the material, but in an undesirable way. So anyways, so in Africa, and by the way, these are fertilizer prices. The prices through which these were generated were taken from the African fertilizer prices, not the international, although it's all on the same website. And so in Africa, a ton of human solid waste processed at 500 degrees would give me $245, mostly from phosphorus and potassium. So the value of thermochemically treated waste is more than 4 times the composted waste. Now, I just wanted to show this just to compare what the international prices are and to show that the value is really different where you are in the world. Like the value of your waste looks different if you're in the United States, where you can buy fertilizer prices using the international market, or whether you're in Africa. So for a 500-degree waste in Africa, you might think that that bag, that ton of material is saving you $245, whereas here it's $61. What's $61? Why would I even bother? And potassium and phosphorus are disproportionately higher in Africa than some of the other fertilizer prices. So in conclusion, pyrolyzed waste at 500 degrees has the highest nutrient concentration and soil conditioning properties. Now, this is not very impressive, but if I just generated an extractable NPK value, I have 0 nitrogen, 0.8% phosphorus, and 1% potassium. Now, again, when you talk about organic amendments, usually they're presented in the total elemental concentration, not in P2O5 or K2O. So, this is not that bad for the extractable. And it has 100% higher nutrients than the compost, 15% higher than the torrefied waste. But now I want to talk about the money that we're getting. So this is what Sanergy sees. This is if I was processing waste, this is the kind of money I'd be making if I was collecting this waste. Well, they are collecting the waste. I don't know, and they are selling the compost and the urine, but I don't really know what they're selling it for. But according to my estimations, those 50,000 people using their toilets who are generating 50 grams of dry waste a day, at a 30% mass recovery for the 500-degree treatment, only give me 0.75 tons of waste. And if this is the price per ton, I only get $190 every day from those 50,000 people. But if I use the 200-degree processing method, I have 90% mass recovery because torrefaction only dehydrates the waste. And I'm assuming I've already dried it down to begin with. This 50 grams is dry weight. So I get a lot more money. I get $582 a day. So I think these values, for a program that's trying to implement this as an intervention, you have to really consider who these prices are for. Are they for the processing plant or the farmer? So my second objective, we've gone over this agronomic value. Now we're going to look at, do different human solid waste amendments affect soil nitrogen and phosphorus in different ways in different soils? And so I incubated them, these amendments, in soils differing in texture and pH. And some of my hypotheses were that I would see a trade-off with the available nitrogen and the available phosphorus with highest heating temperature. There's a lot of literature to demonstrate that, so I thought, well, I would surely see that as well. So I'd lower the products that were subjected to lower temperatures, like the compost and the torrefied waste. They would probably generate a lot of nitrogen, whereas the pyrolyzed waste, especially the 500-degree, would probably have a lot of phosphorus, definitely low respiration, stabilized carbon, and would probably have a high pH. I also wanted to see what would happen if I incubated the 500-degree material, the biochar, with urine, assuming that a lot of this nitrogen isn't available, and I would probably have to offset the lack of nitrogen with a mineral source. Now, in the literature, biochar has been noted to accelerate nitrification through different mechanisms, by having a liming effect, by sorbing phenolic compounds, by providing surfaces for autotrophic nitrifiers. It's also been noted to increase the pH. So if the nitrification process is exacerbating a soil acidity, which could lower the pH, well, I think that adding biochar with that mineral nitrogen should stabilize the pH, generate a lot of nitrate, which is plant available, and keep the phosphorus available. So that's what I thought, that I would not see a negative effect of adding this mineral nitrogen on soil acidity with biochar. I also thought that in terms of the interaction between the amendments I was adding and the soils, I thought that at lower HHT as highest heating temperature, the amendments treated at lower temperatures and the lighter texture, so the sandy soil, would probably promote greater carbon and nitrogen mineralization. I saw that the stable carbon is much higher at the higher temperatures, and in sandier soils, the inclusion of this amendment would probably increase surface area, allow for more microbial activity, so I expected that. And I also expected that there would be greater phosphorus availability when I add the higher heating temperature chars in acidic soils, so that they would buffer the pH, maintaining phosphorus availability. So to start, me and Harold Van Ness, we collected some soils in Western Kenya. It was kind of a wild goose chase, finding the soils that had two soils that had a low pH and a sandy texture, and two soils that had a higher pH and a loamy texture or clay texture. So we collected them from 3 different watersheds. This is the lower Yala watershed, this is the mid Yala watershed, this is the Ninto watershed, and these have been very well characterized by ICRAF and people that have worked here before, like Dori Saltoris and David Gadenya and maybe even Dawit. I'm not sure. They're well traveled, they know this area, maybe they know some people. And so the soil that we collected from lower Yala was an ultisol. Well, these were both ultisols according to the Kenyan soil map, although they were very different. This was a cementic ultisol, like a sandy textured soil. And I performed XRD on all these soils, so I sort of got the fingerprint, the mineral fingerprint, had a lot of kaolite and iolite. This was a very red soil, and it had a coarser texture. It was a clay loam and had a low pH. This soil here was actually a mollisol. It looked like a vertisol. It was like a black cotton soil, and they used to grow a lot of cotton around here. It had an alkaline pH, had montmorillonite, kaolinite, and a lot of oxides, had a high manganese concentration. And a soil that was kind of in the same vicinity, we were lucky. We actually got this is not it's an inceptisol. Sorry, I totally messed that up. Anyways, so this is an inceptisol. So it doesn't have a lot of profile development, but I did have a sandy texture. It was kind of dusty, and it had a fairly non-acidic pH, and it had a very high concentration of extractable manganese. These are the soils we use in our incubation. So the incubation was like a jar within a jar, with another little jar that trapped the carbon dioxide that was coming out of the soil. And so what we did is we incubated 4 different amendments: the biologically processed waste, the torrefied waste, these 2 pyrolyzed wastes, and 4 different soils. These 4 soils that I just described. And I also did a second experiment where I incubated the pyrolyzed waste with urine in excess. So I had the pyrolyzed waste with urine, just the urine and then nothing. And the amendments were added at about a 10 ton per hectare ratio, and they were added on a weight basis, just 0.5% by weight. So they weren't normalized to carbon or nitrogen, they're just added on a weight basis. And the urine was added in accordance with what I would call the resource availability of urine to feces generated from a fresh life latrine. So I just took the proportion of human waste and urine generated on a daily basis, and I added that in that same amount. So I added a lot of nitrogen. I added it in excess. I added about 500 kilograms per hectare, and the urine also contained phosphorus, about 30 milligrams or 50 kilograms of phosphorus per hectare. And I had enough jars to where I could destructively sample at 4 time points, days 0, 7, 30, and 100, during which I tested this trap for carbon dioxide, and I extracted these soils, the whole entire sample, with potassium chloride to get the mineral nitrogen. And this graph is kind of a summary of what I found. So on the y-axis, you can see this is the phosphorus, the difference of phosphorus between day 100 and day 0. On the x-axis, I have the mineral nitrogen concentration, the difference between day 100 and day 0. The shapes of these series, they correspond to these amendments. This upside down triangle is a 200 degree, this diamond is a 300 degree, this forward triangle is 500, the box is a compost, and the star is the unamended soil. And the magnitude of the series is representative of the magnitude of carbon respiration. And this is the ultisol, the sandy ultisol, and this is that inceptisol that has the high manganese concentration. And so what I see is that the lower temperature, indeed, there is a trade-off between highest heating temperature, 200, 300, 500, and nitrogen and phosphorus availability. Although that doesn't really follow through with the compost, which I also would have expected to be down here. Because again, I think the compost is fundamentally different and it's been altered with all the soil that's been added to it. So that's why it behaves just like the soil. And also you see that the shape of this series is much bigger because the nitrogen has been generated through the mineralization of the organic matter. And that's why, not necessarily of this amendment, but in the whole treatment. This amendment promoted the mineralization of a lot of organic matter. And that's why the series is so big, and that's why there's so much nitrogen. Whereas this amendment, it did not promote a lot of mineralization, and phosphorus was not immobilized. But there's still a huge difference between the results in these 2 soil types, even though they are of a similar pH, and even though they are of a similar texture. And I think that's just because of the mineralogy of the soils. So again, I do see this trade-off between nitrogen and phosphorus with highest heating temperature, and I think it's a function of the carbon mineralization, at least in this soil. The compost did not compare to the torrefied waste, even though they were at the same temperature. And I think that the explanation might be the dissolved organic carbon concentrations in these amendments, which happen to be much higher, an order of magnitude higher for this 200-degree torrefied waste rather than the compost. And I think that's probably what explains some of these results. So if a farmer had access to at least one of these, whether this or this, he might get something good. If he just applies the 500-degree material, the difference in phosphorus relative to the control soil adds up to about 22 kilograms of phosphorus per hectare. And these conversions were done assuming a 15-centimeter depth and a bulk density of 1.1. And if he just had this torrefied waste, he'd get about 64 kilograms of nitrogen per hectare relative to the control soil. So that's not bad. And again, I think that the difference between the results in this soil, which has a similar texture and pH to this soil, is the concentration of ammonium oxalate extractable amorphous oxides, aluminum, iron, and manganese, which is about 2% by weight in this soil, and it's 0.5% in that soil. And so there may have been phosphorus fixation here, whereas there may have been microbial immobilization here. Those are just my thoughts. So the second thing I wanted to look at was I wanted to see if I added the biochar with the mineral nitrogen, what happens to soil acidity and to phosphorus availability. So first thing I noticed is that adding biochar with urine did not increase nitrification, or at least didn't increase the amount of extractable nitrate. They were not significantly different in this soil, in this sandy ultisol. And also adding the biochar with urine did not help in terms of the pH. The pH was very much acidified with this urine, and the biochar was even a little worse. So there was no difference in nitrate or pH. The ratios were probably extremely off in terms of the amount of nitrogen I added. But yet the phosphorus availability was not inhibited. So this is the same graph that you just saw with the y-axis was phosphorus, the difference between day 100 and day 0, mineral nitrogen day 100 and day 0. These are the series that I had presented. And these two series are, this is the biochar with urine, this is just the urine. So you can see that obviously we have a lot of nitrogen because we've just added a bunch of nitrogen. The biochar doesn't affect the nitrogen concentrations after 100 days. And the phosphorus is not negatively affected by that exacerbated acidity. So there's still a lot of phosphorus that's available. Although in this soil with the high manganese concentrations, all of these amendments performed very poorly, although the urine by itself wasn't that bad. So there's a very big difference between the soil types and the nitrogen and the phosphorus response. So the conclusions. I definitely saw a trade-off between nitrogen and phosphorus with highest heating temperature, but only among the thermochemically treated waste, not the compost. Probably a function of carbon respiration predicted by amendment dissolved organic carbon. Texture did not play a role, maybe not even pH necessarily, but rather the concentration of amorphous oxides or ammonium extractable oxides. When I added this pyrolyzed waste with urine, did not enhance extractable nitrate, did not mitigate acidification, although phosphorus did remain unaffected, which is good. So maybe this is a good amendment. Maybe pyrolyzed waste in urine is a good amendment, although we still obviously have to deal with the acidification. So the last thing I'll talk about is, so we've gone over some agronomic properties and values. We looked at nitrogen and phosphorus availability. And now we're going to talk about whether we can increase the value by incorporating the mineral nitrogen in urine into the pyrolyzed waste, so not just adding it as a separate liquid, but sort of intercalating the nitrogen into the matrix so we can apply it as a granular fertilizer. So to that end, we've been trying to develop a process for precipitating urine nitrogen into pyrolyzed waste. Urine, it's everywhere. So our goal in combining mineral nitrogen in urine with biochar, again, I want to emphasize that most of the nitrogen is in household waste is in urine, and most of this nitrogen, about 90%, is mineral. It's plant available, whereas the nitrogen in solid waste is very little, and it's generally organic. And the species of nitrogen urine is urea, which will hydrolyze immediately in soil and in a container that is sort of used often with urease into ammonia. And during that process, the pH will go from about 6 to 9. And at 9, you'll end up having about half ammonia and half ammonium. That's why urine can smell really bad. And that's other reasons. But and so when you talk about like loading nitrogen onto the biochar matrix, you're dealing with two different forms of nitrogen. You're dealing with ionic ammonium, and then you're dealing with very reactive ammonia, which can be dissolved in water or it can be in a gaseous form. So I'll just go over a few of the mechanisms which are of interest in trying to develop this process. You could just have nonspecific physisorption. You could just have nitrogen, ammonium or ammonia, just sort of being trapped in the pore spaces of biochar. We all know that biochar is renowned for its surface area, for microporosity. So you could just be retaining nitrogen through occlusion in pores. But the only caveat is that since the diameter of ammonia is about 3 angstroms, you need to have pores that are of a similar magnitude, maybe 10 to 15, 10 to 20 angstroms, or else these van der Waals forces are not going to be effective at all. And honestly, I don't know what the microporosity of my char is. I am assuming it's mesoporous. That may not be very important of a mechanism. Another factor that that we understand from soils is cation exchange capacity. We could have a retention of ionic ammonium, also weak bonds on deprotonated hydroxyl groups on anions, maybe sulfur, maybe phosphate. We could also have retention of ammonia, which through strong sorption on Bronsted acid groups. So because we know that ammonia has these free electron pairs that can either receive a proton, and that is a strong sorption, or it can actually interact with, for example, in this carboxylic group, the oxygens have created a dipole. So this is very nucleophilic. This is electrophilic, and so this ammonia could essentially bond in this carboxylic group and form an amine group. So this is possible. And so this is strong sorption. This is no longer extractable nitrogen, but it could probably be easily mineralized in soil. So these are different mechanisms that we can have. But again, I was mostly interested in just pushing this to the max. I was like, forget all these surface functional groups. I just want to precipitate an ammonium salt on the surface. I want to get this. I just want to get a whole bunch of nitrogen on the surface that we can just put in the soil. So ammonium salts, you have many ammonium salts. You have ammonium sulfate, you have struvite. That's something that people have looked into. Struvite is ammonium magnesium phosphate, and it often just precipitates in wastewater streams, precipitates in pig manure. But the problem with some of these other ammonium salts is that you're going to have to import this counter ion. But since we're dealing with pyrolysis, we have a counter ion. We have bicarbonate, because we have carbon dioxide. Carbon dioxide is a waste product of pyrolysis, right? And since urine is a pH of 9, if we inject the carbon dioxide into the urine, we can speciate it as bicarbonate, probably not as carbonate. So I'm just saying that I thought, well, bicarbonate, maybe that's a good counter ion, because anyways, we don't want to spend more money on some of these other things, on like sulfate or magnesium. So anyways, but we're just going to go back now. We're going to go through some of these sorption mechanisms and look at what we have. Okay, so now we're going to look at end loading via physisorption and cation exchange, sort of like Lewis acid-base interactions on oxygenated functional groups on the 500-degree material. So when I talk about sorption mechanisms, I want to maximize all the portfolio of options, because again, I have different types of nitrogen. I've got this heterogeneous surface, biochar. So here on this y-axis, I have the surface area of different human waste that's treated at different temperatures. Here I have the compost, the torrefied waste, the 300, 400, 500, 600, 700. This is the surface area, meters squared per grams. You can see it goes up with temperature. Here I have the cation exchange capacity, millimoles of charge per kilogram, and it goes down because as the material is heated, you have a loss of these functional groups with heating temperature. But since I'm trying to diversify the portfolio of options for sorption, I want to get into this sweet spot area. I want a little of everything. So I'm going to go with the 500 degree. I'm going to say, I'm focusing on this. This is what I'm going to use to load up the nitrogen, because look, if I can take this value, the surface area value, and I can convert it to how many potential moles of ammonia I can get. And when I do this conversion, maybe I can even get an increase in 4.3% of mineral nitrogen on the surface just through physisorption. But again, you have to remember that this requires micropores, and I really don't know if I have, I have not yet calculated this data. So we'll put that on hold for now. In terms of electrostatic sorption mechanisms, it doesn't seem like the CEC is promising me a lot of retention of nitrogen. The amount of ammonium I can retain, so it should be ammonium, is only increases my mineral nitrogen content by 0.31 percent point. So it doesn't look very promising. So why don't we just look at the total potential of sorbing nitrogen through these acid-base interactions, whether strong sorption or weak sorption. And I'm going to say, I just want to look at the oxygenated functional groups as a proxy for how much I can even get. So here I have this FTIR spectra from wood and oxidized wood, which have a high proportion of oxygenated functional groups, which can absorb ammonia or ammonium. And then I have my char, the human solid waste. These are all pyrolyzed at 500 degrees. This was oxidized after pyrolysis. So here I have this carboxylic point at about 1700 wave number. And you can see that in the oxidized wood, it's very strong. It's kind of, there in wood, but it's very absent in my char. I just don't have, this is not a material, it's not like wood. It doesn't have these sort of oxygenated it doesn't have these kind of functional groups in the same proportion. Here's a phenolic peak here for OH and CO. And again, I can see it with wood, but I really don't see it in my char. The opposite, I actually have this amine peak because I have so much organic nitrogen. So honestly, looking at the spectra, I'm like, I don't really know if this material is gonna really sorb ammonia or ammonium through these interactions. But I said, okay, let's put that on hold for now, and let's just do an experiment. Let's just take a bunch of urine, and we're gonna take some biochar from Sanergy, and we're gonna mix it all together, and we're gonna look at how much nitrogen we can actually sorb onto the biochar. So I took some fresh urine from Sanergy, I acidified it to a pH of 6 to try to get all the nitrogen as ammonium. I took some fresh urine that was already at a pH of 9 through that, through the urease interaction, and then I had a controlled deionized water. I just added the biochar made from Sanergy at 500 degrees. This was the ratio I added it at, and I determined the nitrogen loading by combustion on a CN analyzer at ICRAF. And so what did I see? I saw that the acidified urine was the only treatment that actually gave me a little bit increase in nitrogen. I got a 1.1% increase in total nitrogen, assuming it's mineral, after this experiment. So that means that I was probably retaining ammonium, because most of the nitrogen was speciated as ammonium. And this actually is greater than what would have normally been predicted by cation exchange capacity. So there must be some other mechanisms at play. So now I'm going to move on to what I thought might be more promising, and that was trying to precipitate a nitrogen salt onto the surface of the biochar, basically using the biochar to nucleate these salts. And so I had a system where I had these jars, and I made these suspensions with this concentrated nitrogen solution, like a synthetic urine solution, and I added a bunch of biochar. I injected carbon dioxide. I did a whole bunch of different configurations of this experiment to see if anything would precipitate. And what I ended up doing is I raised the pH of this very concentrated ammonium chloride with sodium hydroxide so high, and did this injection with carbon dioxide, that I actually got sodium bicarbonate precipitation. It was very strange, but that was not what I wanted. So anyways, I eventually settled on that I really needed to start moving towards working in the gas phase. And I probably should have done this with ammonia, but I didn't. I kept ammonia in solution, because I think that water, especially since the solution was at a pH of 9.25, ammonia, similar to water, can form hydrogen bonds. So water is probably interfering in all of these potential interactions. And so I probably need to move towards working in the gas phase. So I use 3 different types of biochar. I use wood, unoxidized wood. Oh, sorry, this is oxidized wood. And I used the human waste. They were all pyrolyzed at 500 degrees. And my final configuration was I immersed the char into this concentrated nitrogen solution for half an hour. And then I filtered it, and then I flushed carbon dioxide gas over the surface of the char. And what I was hoping to do was to sequentially sorb ammonia, and then on the amine functional groups that I thought I might be incorporating, sorb carbon dioxide, and then maybe I could sorb ammonia. I was trying to do this whole thing, and it didn't really work out. So what I got, so I was trying to eventually basically get the precipitation of ammonium bicarbonate through the sorption of these counter ions. So what I saw was that on the y-axis of this graph, I have the percent increase of total nitrogen from the exposure to the urine solution. And here I just have these categorical variables of carbon dioxide, exposure to carbon dioxide gas and nitrogen gas, which is just the control. And I have these 3 different materials I use, my human solid waste char, the oxidized wood, and the unoxidized wood. And I saw that there was no significant difference in the amount of nitrogen that was loaded onto the char. This was measured by combustion. at sea now. I mean, you can sort of like, you're like, oh, that's kind of a trend, it's kind of moving up, you know, and maybe that's true. And I do think that if I need to reconfigure this, and I think I might be able to actually see what I'm trying to see, but as it stands, I was definitely able to increase the nitrogen concentration and all of the just exposure to nitrogen to this concentrated solution for a pretty short time. I was able to increase the total nitrogen, which I'm assuming is mineral from that solution, by between 2.6 and 5%. Evidence of a slight increase with carbon dioxide, obviously not really, but kind of, you know, and then there could be interference with water. And so I think that we just need a different experimental design. It's not the right way to do it. So, and I just wanted to just show one last thing, was I then took these chars back and went to CCMR, and we looked at the FTIR spectra of these 3 different chars that I've already shown you before. So the blue line are the control. These are the spectra that you already saw, just the chars without exposure to anything. The red line are the chars that were immersed in the solution and then exposed to carbon dioxide through this flushing. And the green line are the sort of like the control chars that were immersed in the solution and then exposed just to inert nitrogen. And what I saw was that in all of the chars, I was able to distinguish that there were 2 new peaks that formed at the 1400 area and at the 3000 area here, this area here, in all of the materials, sort of more prominent in the oxidized wood. And this 1400 peak corresponds to ionic ammonium. So either this is sort of crystalline on the surface or electrostatically absorbed. Other people would know better, like Anita and Mike. I'm just a novice, but I'm learning. And then these 2 peaks are, so what I learned is that these 2 peaks together can be indicative, these 2 fangs of an amine. And I did correlate that this one website, this other website, that at this I could have the incorporation of amine functional groups, sort of through what I had shown you about that Bronsted interaction, this ammonia adsorbing to these functional groups through this nucleophilic addition and forming these amine groups. So I think that here I might be seeing ammonia sorbing, and here ammonium, and here I might be seeing ammonia sorb, because remember the pH was right at the pKa, so I had both species in solution. And so that's very interesting, because I think with my carbon dioxide thing, I need more of these functional groups to get this to work. Anyway, so that is my FTIR data. And so in conclusion, I just want to say that, despite fewer proportion of carboxyl and phenolic, another thing I noticed, I was going to say this, was that there's a phenolic peak in the wood that here at about 1200 that disappears after exposure to nitrogen. It's not, you don't really see it in the human waste because I didn't really have that to begin with. Anyways, despite fewer proportion of carbox and phenolic groups, human solid waste sorbed about 3%, mineral nitrogen 2.6, more than the CEC predicts. Possibly, you know, I don't know if it's through physisorption, so is this precipitation? Or, you know, maybe it's some other things. So I'm just looking at these mechanisms. So anyways, and so in conclusion, I just want to say that the pyrolyzed waste doesn't seem chemically poised to retain ammonia or ammonium based on acid-base interactions, unless by metals, because initially the FTIR spectra showed a low proportion of oxygenated functional groups and CEC. However, we are retaining both ammonia and ammonium. So urine absorption showed retention, this first experiment, of ammonia. The FTIR reported to the incorporation of amine groups, probably through ammonia, and precipitation was not observed visually. Might not be possible with water, in solution. So in the end, we achieved N loading by 2.5 percent points, giving us our total extractable NPK of 2.5, 0.8, and 1. It's not bad for an organic amendment. I said it's worth further iteration because remember Kibera and the maize trial. And so I just want to thank, so I'm done. And I just want to thank my advisors, Johannes and Harold, Rebecca Nelson, and I put Beth Medvecki. She was, I worked with her in the IGERT, and she's a good friend of mine. And people at Sanergy and the Climate Foundation, Fausto and Brian, and obviously people in Johannes Lehmann's lab, especially Akio and Kelly and Dory and Rachel, who helped me through so many things. And everyone else, it's been so amazing. Alyssa Kirsch, with whom I did a lot of these other experiments, she's an undergrad, and others, Murray McBride, when I TA'd for him, I would always be like, what about the nitrogen? and Janice, Shai, Rio over at Frank DeSalvo's lab, Mike for helping me interpret the spectra, Jonathan, Kathy Howe, all these people at University of Nairobi, and CNAL, because they let me like run their machines and mess everything up, and Hugh, he did an analysis. So I just want to, and also the funding from the IGERT, poverty reduction, and all these different things. So thank you very much. Yes?
You mentioned in the very beginning that xenobiotics are not an issue in pyrolysis.
Yeah.
I was just wondering if you could expand on that a little bit and explain why that's the case and maybe how that would compare to compost.
Yeah. Okay. So, I really can't speak from empirical results. I've never tested this, although we did test PAHs and dioxins, and they were not in the chart. But in terms of xenobiotics, I'm just assuming that if you go up to 500 degrees, I'm assuming 300 to 500 degrees, you'll probably have the transformation of xenobiotics, probably aromatic rings fusing together. Now with urine, it's another story, and so that is a concern because you can pasteurize urine very easily. You can get rid of the pathogenic organisms at about 70 degrees Celsius, but we know that urine has xenobiotics. So actually the process that I'm interested in now looking at urine is trying to sorb nitrogen from the gas phase, and so you just avoid the whole issue of xenobiotics, because that is a problem. Yeah.
I'm wondering about salt. If you apply a lot of urine and
Yeah.
the soil, you're adding a lot of salt to the soil.
Yeah.
Pretty far up,
Yeah, you're right. And in this paper that I'm writing on the value, I want to subtract from the value the contribution from sodium, because it's a deterrent. Well, this is from the charred waste. There's also sodium in that. Yeah, that's why I think that there are some issues with obviously with sodium. And I was looking at trying to concentrate urine using porous membranes, and you can get membranes that can allow, because sodium is a little bit larger than ammonium. And so that's been in the forefront of my mind. Like you have to prevent sodium, because even if you don't have heavy metals, that can ruin everything. Yeah, I agree with you on that.
Yeah, thanks. I was just curious with your kind of initial part of the sort of producer-based or consumer-based value, if you looked at transportation costs at all?
No. No, I need to, honestly, I'm still figuring out to what extent I want to, how far the cycle should go. But I think that's very important, transportation costs. I haven't incorporated that yet. I think it's important. I was trying to keep it really simple, but I do think that it's difficult to make an argument if you're not even considering how to get the material to the people that are growing the crops. I have to really consider that.
Great. And with that, I think we're out of time.
Thank you.
This has been a production of Cornell University, on the web at cornell.edu.